Hi, glad to have you along. In this video, we're going to be discussing how you use properties of exponents to simplify expressions. And the goal, you see, is to use properties of exponents to simplify expressions involving powers. Now, just a little background here. I'm intending this video for my Algebra 2 level students, and so I'm actually assuming that you've had a little exposure to the properties of exponents that I'm going to discuss here, and that this is a review for you, and maybe exposure to some not really difficult, but some more difficult examples of all the properties that we're going to be learning. All right, so a little disclaimer there. Let's get right into the lesson. And even though I am assuming that you have a background in powers and simplifying expressions with powers, I do want to start off with a basic question that I think many of you don't know the answer to, and that is, what is a power? Now, many of you think that power and exponent are simply interchangeable words, and you're really not going to go astray if you believe that. But I do want to try to explain that there is a difference between the two. It turns out that a power is an expression that has a base and a variable, or it's an expression involving exponents. This entire expression here, a to the m power, is a power. Okay? Now, a power, as I was saying a moment ago, always has to have a base and it has to have an exponent. Those are the two parts of a power. And not a lot beyond that. I just want to make sure that you know that a power requires both of those things, the base and the exponent. All right. Now let's learn some properties of powers. Or rather, properties of exponents that would apply to powers. And we're going to start off with two properties that I think that you know quite well. And those properties are called the product of powers and the quotient of powers. And you see in this first example here, I have one power times another power. And I think that you are aware that whenever you multiply two powers with the same base, that you simply add the exponents. So a to the m power times a to the n power would be equal to a to the m plus n power. So its simplest example could be something like x to the 7th times x to the 19th power is equal to x to the 26th power. Always add exponents when you multiply powers with the same base. Okay, now a little thing that I want to emphasize to you along with that is that you do have to have the same base. If I had, say, 4 to the 7th power times 3 to the 2nd power, well, I can't add the exponents right there. I can't say that that's equal to 12 to the 9th power or anything like that. Okay? That whole thing was wrong. Only works if you have the same base in those powers. Okay, and then similarly, the quotient of powers property would apply to whenever you're dividing two powers with the same base. In this case, the base is m in both of those. And as you either know or would probably guess, even if you didn't know, whenever you divide powers with the same base, you do the opposite of what you would have done when you multiplied powers with the same base, and that is that you subtract the exponents. So if I had 21 to the 19th power divided by 21 to the 15th power, that would be equal to 21 to the 4th power, because I just had to subtract the exponents to make that happen. Now let's look at some examples where we're going to apply those particular properties. And you see several examples on your screen. First, you see 5 to the 7th power times 5 to the negative 3rd power, and as we were saying a moment ago, whenever you multiply two powers with the same base, as is the case here, you're going to add those exponents together in order to simplify that expression, and 7 plus negative 3 is going to give you 4. And right now I'm really focusing mostly on you being able to apply the properties of powers, but it's good if you're actually able to simplify some powers of real numbers. And 5 to the 4th power, 5 times 5 is 25, times 5 is 125, times another 5 is 625. That would be the simplest form for that particular expression. Okay, now in the second example here over at B, I'm taking the same powers, but this time I'm dividing them. And we've said that whenever you divide powers with the same base, you subtract them. So that would be 5 to the 7 minus negative 3 power. And 7 minus negative 3 is 10, so you'd get 5 to the 10th power. Now sometimes these values get too large for us to really worry about. 5 to the 4th power was not a ridiculously large value for us to simplify. 5 to the 10th power, we're probably getting there, so I'm just going to leave that in that form. Now, a couple of more examples just to make sure you're understanding these properties and how they apply, maybe in some more difficult situations as well. Let's look at C. I'm actually going to end up using both of those properties in this particular example. In the numerator, you see I have 10 to the x power times 10 to the 6th power. Now, you might think, what in the world can I do with I have a variable for an exponent? But in terms of this problem, what's relevant is the fact that the two powers that I'm multiplying have the same base. They both are base 10. And so what I'm going to do is I'm going to add the exponents. And since I don't know what x is, that means when I add those two exponents, I'm going to get x plus 6. So I'll have 10 to the x plus 6 power over 10 to the 8th power. Now again, you might say, I don't know what x is, so how am I supposed to divide these two things? Well, again, we're dividing, and the powers, or the bases of those two powers that we're dividing are the same, so we get to subtract the exponents, and when we do so, we'll get the same base as we had, but just now we'll get the difference of those two exponents, and x plus 6 minus 8 is x minus 2. All right, hopefully you're getting this. Now, last example here. You're going to see in the numerator, first of all, I do have 3 powers that I'm multiplying, but only 2 of them have the same base. And so what I can do is take those 2 that have the same base and add their exponents. I can make that 2 to the 13th power, and then I can't really do anything with the 3 to the negative 1st power for right now. And the denominator, well, neither one of those powers have the same base, so we'll leave that alone. And then what I'm going to do is go ahead and separate this into 2 different quotients. Or, well, essentially. I'm going to do 2 to the 13th power divided by 2 to the 2nd power. Well, that's dividing powers at the same base. That gives me 2 to the 11th power. And 3 to the negative 1st power divided by 3 to the negative 3rd power. Negative 1 minus negative 3 is 2. So we'll get 3 to the 2nd power. Now, 3 to the 2nd power is 9. That wouldn't be a ridiculous thing to actually go and simplify. 2 to the 11th power, that might be a rather large. And I wanted you, again, just to focus on the properties that we're applying there. So hopefully you've got that. Good. Let's move on to some other properties. Now we're actually going to learn 4 properties here on this particular slide. We're going to go 2 at a time though. And we're going to begin with the power of a power property. And the power of a power property is exactly what it sounds like. It's when you take a power, in this case a to the m, and you raise that to another power. Okay, now I was saying a power has to have a base and an exponent. The first power of the base is a and the exponent is m. The second power here, this whole thing is the base and this is the exponent. Now how do you simplify an expression when you're raising a power to a power? Turns out that you multiply the exponents when you do that. So we would make that a to the m times n power, which is easily illustrated if I took something like 2 to the 2nd power to the 3rd power. Well, of course, if you raise something to the 3rd power, it means you would multiply that value by itself 3 times. So that would be 2 squared 3 times, wouldn't it? And then if we used our power or product of powers rule and we added all those exponents, you would get 2 plus 2 plus 2 is 6. That we could have skipped the step where we separated this into a long multiplication problem if we just would have multiplied those 2 exponents together. Yeah, so power of a power, you just multiply the exponents. All right, and the 0 exponent, you don't get much simpler than this. Any number to the 0 power is equal to 1 except for 0. You can't raise 0 to the 0 power because 0 to the 0 power is actually undefined. Great. So there's a couple of properties I wanted you to know, and a couple of other properties that we're going to work with right now would be these: the power of a product and the power of a quotient. Now, a power of a product is when you're multiplying 2 values. In this case, we're going to say a and b, and then after you find the product of those 2 numbers, you're raising that to a power. And so it turns out whenever you have the power of a product, what you could do is you could raise each factor in that product to that power. So I could think of that as being a to the m power times b to the m power. Some people call that distributing the exponent. It's really not distributive property, but that's a way to kind of imagine that power of a product property. So for instance, if I had 3 to the 2nd power times 2 to the 4th power. Whoops, well, let's make that a little simpler. Let's say I had 3 times 2, and I wanted to raise that to the 3rd power. Well, I could make that then 3 to the 3rd power times 2 to the 3rd power. And that would be 27 times 8, or 216. And I picked that example because you could have actually done 3 times 2 and gotten 6 to the 3rd power, and 6 to the 3rd power is 216. So with that example, you were able to see how the power of a product property actually does work with regular numbers. Okay, then there's the power of a quotient property, which is very similar to the last property that we just did. Anytime you have a quotient and you're trying to raise that quotient to a power, you can raise the numerator of that quotient and the denominator of that quotient to that power separately. Excellent. Let's see some examples. And I'm going to try to work in as many of those properties as I can in just a couple of examples. All right, you see, first of all, I've got a product right here, and it's a pretty big product, manufacturers, being raised to a power. All right, and so what we have said is that if you're raising a product to a power, you raise each factor in that product to that power. Now, a couple things I want to point out to you here that are common misconceptions. A lot of people would say, for instance, that this 5 for the 4p to the 5th belongs to both the p and the 4. But any factors that don't have exponents written directly after them are implied to have an exponent of 1. So that's not 4 to the 5th power, that's actually 4 to the 1st power. And similarly, this q that doesn't have an exponent directly after it, well, that would be q to the 1st power. All right, now I'm going to kind of write this out the long way. That would essentially mean that we have 4 to the 1st power to the 2nd power times p to the 5th power, I meant to the 3rd power, excuse me, over here, to the 3rd power, because I'm raising each factor in this product to this power. And I'll continue on. Then times q to the 1st to the 3rd power, times r to the 2nd to the 3rd power, and times s to the 0 to the 3rd power. Okay, now that makes this then 4 to the 3rd power, and because whenever I raise a power to a power, I multiply the exponents, right? 1 times 3 is 3. Here, 5 times 3 is 15, so p to the 15th power. And then q to the 3rd, r to the 6th, and then s to the 0 power. And then that's mostly simplified already, except that we happen to know that 4 to the 3rd power is 64, and that's a reasonable one to simplify, so I did. Can't do anything with the p to the 15th power, or the q to the 3rd power, or the r to the 6th power. But we've also said that anything raised to the 0 power is 1, and so we're going to assume that s to the 0 power is 1, and I don't really need to write times 1 at the end of this product. All right, so lots of factors there in that product, but I think that you understood the process that we went through. Okay, then for part B, we're raising a quotient to a power. And we said to raise a quotient to a power, or a fraction if you prefer to say it that way, you raise the numerator and the denominator both to that power. So here I would have to raise 5m to the 4th to the 3rd power, as well as 2n cubed to the 3rd power. All right, now within that, I've also created a situation where we're going to have to raise a product to a power. And so we said we're going to raise every factor in that product to that power. And that means here we'll have 4 times 3, or 12, m to the 12th power. Here that's 2 to the 1st to the 3rd power, so 2 to the 3rd power. And then into the 3rd to the 3rd power, we'll multiply and we'll get into the 9th. And so that's 125 m to the 12th over 8 n to the 9th. All right, only one more property that I want to discuss with you, and so let's get right on to that. And the last of those properties that I want to talk to you about is the property that belongs to negative exponents. Now, when you have a negative exponent, very simply, this is a process that you follow. A negative exponent tells you to take the reciprocal of the base, and the reciprocal of a would be 1 over a, and then raise that to the positive m power in this case. So whenever you take the reciprocal of a base for a power, you always change the exponent, the sign of the exponent then. So 1 over a to the m power. Now, if we go ahead and follow our power of a quotient property, then that becomes 1 over a to the m, or 1 to the m over a to the m power. And since 1 to the m power is 1, because any power of 1 is 1, then that just becomes 1 over a to the m power. So really, I could have said the simplest way of writing a to the negative m power would be 1 over a to the m. Now, a couple quick examples of that power being put into practice before we do some more complicated examples possibly. Let's say that I had 2 to the negative third power. Well, the way I'm going to handle that negative exponent is first of all taking the reciprocal of the base of that power. Reciprocal of 2 is 1/2. And then that changes the exponent to positive. And so we can use the power of a quotient property again here. 1 to the third is 1. 2 to the third is 8. Voila, there we go. Okay. And the reason I like to emphasize the taking the reciprocal of the base thing is for especially whenever you have fractions being raised to a power. So suppose we had 2/3 being raised to a negative second power. Well, to take care of the negative exponent, we're going to take the reciprocal of the base of that power. So 3 squared, and that'll change the exponent to positive. And then we can do 3 squared 9 over 2 squared 4. Voila, we've got it. Let's take a look at some more complicated examples. And in these examples, I'm going to try to tie together as many properties of exponents as I can from the ones that we've already discussed. And we'll also try to talk about order of operations and that kind of thing here. Now, of course, if you were going to try to simplify an expression that had parentheses and exponents, you would start inside the parentheses. But since we don't know what k is, we can't raise it to the second power. And similarly, we can't multiply 6 times k squared because, again, we don't know what k is. So what we're going to have to do then is we're going to have to start off with the power of a power property. We're raising this, and the product of a power. We're raising this product to the negative third power. And so we're going to raise each factor in that product to the negative third power. So that'll be 6 to the negative third power times k to the negative sixth power. Because remember, you have to multiply the exponents there. All right, and then how does that work? Well, we're now going to go ahead and raise 6 to the negative third power, and that would be 1 over 6 to the third power. And then k to the negative sixth power, that would be 1 over k to the positive sixth power. Now our numerator, 1 times 1 is 1. Denominator, this is 216 times k to the sixth power. All right, not so bad, I hope. Here I've got a quotient being raised to a negative exponent. Well, I can't do anything inside the parentheses really, and so what I'm going to do is I'm going to start with the negative exponent, and that means I need to take the reciprocal of the base, and that's going to give me then 3b to the third power over 8a to the fifth power, and that whole thing will now be raised to the positive second power. And I think you'll see how I get from there to here. Then I have 3 squared, 9. B to the third squared is b to the sixth. 8 squared, 64. And a to the fifth squared is a to the 10th. A couple more examples here. Another power of a product. Now, I'm going to start inside the parentheses, and I'm going to do a couple things inside the parentheses. First of all, I hope you notice that there actually is a little bit of multiplication that can be done, because even though I can't multiply all these values together, 2 of the factors have the same base. And so I can take that x to the 4 times x to the negative fifth power and make that x to the negative first power. All right, then the next thing I can do is this. 2 of those 3 factors that I have remaining still, happen to have negative exponents. And so what I'm going to do is I'm going to move those to the denominator. And I have one of those factors that has a positive exponent, and I'm going to leave it right where it is in the numerator. So let's make that z over x to the positive first power, y to the positive second power, and I still have that being raised to the negative third power. All right, well, now I'm ready to raise whatever's in here to this negative exponent, so I need to flip it. Let's make that xy squared over z, and that's going to change the exponent to positive. And then let's raise each factor in that quotient and product combination up to the third power, and we'll get x cubed, y to the sixth, z to the third. Final example. I've got a quotient with a bunch of variables here. Now, I'm going to use what one of my old teaching friends used to tell her students in order to explain this one to you. She had a way of storytelling in order to teach her students, and the story that she would tell when negative exponents were involved was simply this, that, and especially this involves fractions, anytime you have a negative exponent, that means the factor with that negative exponent is unhappy where it is, meaning if it's in the numerator, it's unhappy there, and if it's in the denominator, it's unhappy there. Whereas any factor with a positive exponent is quite happy where it is, and it's going to stay there. So, what we're going to try to do is we're going to try to make every factor in this expression happy, and the way to do that is to take any unhappy factors like this q here and this p there, and to move them to the opposite of where they are. In other words, this q to the negative seventh power, we're going to move it to the denominator, and this p to the negative second power, we're going to move it to the numerator. I don't think I actually want to write it where I was going to. Let's just do this below. Alright, so let's consider all the different factors here. 24 is to the positive first power, so it's happy where it is, it's going to stay there in the numerator. P to the fifth power, happy where it is, it's going to stay in the numerator. We're going to move the q to the negative seventh down. However, we are moving this p to the negative second power up to the numerator, and it's going to become p to the positive second power. And then the r has a positive 1 for an exponent, so we'll just leave it where it is as well. And then for the denominator, well, the 2 to the third power is happy where it is, and in fact, let's go ahead and call that 8. And then we said we were moving this q to the negative seventh power down here, and when we moved it down, it became happy. And then we still had this q to the positive first power that was happy where it was already. A little bit more that could be done here. Alright, I'm going to start with the non-coefficients first. I've got a p to the fifth times a p to the second in the numerator, so I can make that p to the seventh power. And then that r is going to stay there. In the denominator, q to the seventh times q would be q to the eighth power. And then the final thing that I'm going to do right here is simply use my rules for simplifying fractions, in which if a numerator and a denominator have a common factor, as 24 and 8 do, you can go ahead and divide them both by their common factor to simplify. And so we're going to end up with a 3 p to the seventh r in the numerator, and then we don't really need to write the 1 that would be down there in the denominator. Okay, that's a lot of work with exponents. I hope that you found all those rules simple enough, but I needed to show you lots of good examples where you apply those different properties. Hope this has been helpful to you. Talk to you next time.